The first topic in looking at advantages of feedback that we're going to examine is to see how well a feedback system responds when there is a disturbance in the system versus how well the open loop system responds when there is a disturbance in the system. And in particular, we're looking at some kind of step-like disturbance. And on our motor example, that would be like adding a constant load torque where there had been no constant load torque to begin with, or removing a load torque when there had been a load torque to begin with. So some change in load torque that has a stepwise behavior. And we know that we can model steps with the function 1 of t. So what we're going to say is if the input to the motor, EA, is a constant, and if the load torque is W times 1 of t, a constant, then we're going to look at what is the steady state output of the system. And we're not interested at this point in the transient response, so when the load torque is added, there may be some ringing, but we're looking at when time gets large, way out here somewhere, is the impact of the load. I've got a desired signal here. Does the load make me have some offset between the desired and the actual response because I just can't get there? So if we're looking into the far future, if we're looking into the steady state regime, a theorem that is extremely helpful with this is the Laplace transform final value theorem. You see, if we didn't have this theorem, what we would have to do is we would have to bring all of our Laplace domain information back to the time domain, would have to solve for, well, what is the output in time domain as a function of t, and then let t get large and examine the function as t gets large. But thankfully, there's a theorem that says that we can use Laplace transforms to find this out without actually ever going back to the time domain. So the Laplace transform final value theorem says if a signal has a constant final value, we can find it as y sub ss, where ss stands for steady state, is the limit as s approaches 0 of s times y of s. Now we have to be careful because there's an if. We have to know that this theorem applies in some cases, but not in other cases. So when does this apply? And so this is what the note says. A signal has a constant final value if and only if, this is not a typo, that's the mathematical symbol for if and only if, all of the poles of y of s are strictly in the left half s plane, except possibly for a single pole at s equals 0. So what we're going to do is we are going to have to look at y of s and where are the poles. If the poles are there, there will be a constant final value. If there's one pole there, I will still have a constant final value. If I have two poles there, all of a sudden I don't have a constant final value. I have a system that has output that keeps on increasing forever. If I have a pole somewhere on the imaginary axis, I don't have a constant final value because it's going to oscillate forever. And if I have a pole on the right half S plane, I also don't have a constant final value because the output keeps on increasing and possibly oscillating while it does so. So we have to check that all of the poles are in the left half plane except possibly for one pole at S equals 0. Now, if you're really clever, you'll have noticed that this here is actually looking to see if there is a pole at S equals 0, and it's looking for the residue of that pole using an inverse Laplace transform partial fraction expansion idea. So what it's doing is it's saying that y of s is equal to a summation of, say, A over S plus a summation of poles terms, and it's looking for that value A. And we know that the y of t that corresponds to that, the 1 over s term is a step, and that A multiplies it, so that's going to be my final value if all of these other poles decay to 0 because they're stable. So the final value theorem is not magic, it's just, in fact, partial fraction expansion. For the input signals that we have chosen, we have said that EA of t was the constant EA times 1 of time, and we know that 1 of t has Laplace transform of 1 over s, so EA of s then is just the number EA divided by s, and similarly W of s is the number W divided by s because we have a constant step-like disturbance that we have assumed. So we go and we look at the expression that we obtained for y of s in the previous section of notes, and we substitute that into the final value theorem. First, does it apply? Well, let's look at it. This is y of s inside of these brackets here. Y of s has 2 parts, and because they add together, I could even think of the 2 parts separately and add them together. The limit distributes across the sum. So looking at the first part, I've got a pole at s equals minus 1 over tau 1, and as long as tau 1 is not equal to minus infinity, I guess, then I have a pole that's not at the origin, and so any reasonable value of tau 1 gives me a pole on the real axis somewhere, not at the origin. Similarly for tau 2, and I do have a pole at the origin. There's my 1 over s pole, so there will be a residue because of that. And the same is true because in the other term that is caused by the disturbance input, if we look at that, I've got the tau 1s plus 1. That's a pole somewhere on the real axis. And I've got a tau 2s plus 1 somewhere else on the real axis. And then I've got the w over s. That's a pole right there. So the final value theorem's criteria is satisfied. And we can apply the theorem, which says take all of that, take all of y of s, multiply it by s, and take the limit as s goes to 0. And we know that when we're taking limits, that has the lowest order of operations. We always take the limit last. If there's any kind of cancellation, then we can do that first, and in fact there is. So the s here cancels the s there and there. And as we let s go to 0 after that, the tau 1s just becomes 0, tau 2s is 0 in 2 places. And the first term is a times EA divided by 1, and the second term is b times w divided by 1. So there is a steady state output. And if we look at this, this is the response of our open loop system without a controller. We haven't done any feedback. All we've done is we've input EA into the system, and this is the steady state Y that we get. So let's make a simple open loop controller. And here is the block diagram of how we want to think about this. It's a little different from the one I drew before, but they are in fact equivalent block diagrams, as you can confirm using some block diagram algebra if you like. We have the motor, we'll say, has transfer function A over tau 1s plus 1 and tau 2s plus 1. And then the disturbance input, W, comes in, and it has this scale factor B over A. So if you think about it, this EA is multiplied only by the motor block, but the disturbance is multiplied by the motor block and B over A. So the disturbance is B over A times A over the denominator. The A's cancel. I get B over denominator, which is exactly that term right there. So this works. This is a valid block diagram. So when we're designing the open loop controller, we're at this point only going to consider a gain. So our open loop controller is an amplifier, and I have to choose some value to amplify R of t by, and in the absence of any other brilliant idea, I'm going to choose the value of the controller such that if there's no disturbance, I get the best performance that I can get. So let's look at this. I'm going to have EA is some constant, that's my gain factor, times the reference input. OL stands for open loop. And we'll choose K open loop so there's no steady state error when the disturbance is 0. So Y steady state then is A times EA, but EA is K open loop times R. That gets substituted in there, plus B times W steady state. But when I'm designing my controller, I'm going to say I'm looking only at the case where W equals 0. So for design purposes, that goes away. And then I have to say, well, I want Y steady state equals R steady state. So then that this here is going to equal R steady state is my goal. I divide both sides by R steady state. I get 1 equals A times K open loop, or K open loop is 1 divided by A. That's our controller for that. So we can go back to this previous page here and say, oh, well, we've designed this. This is now just 1 over A. So the question is, can we do better than this in a closed loop configuration? And here is our block diagram. This part of the diagram has not changed at all, but what we've done is we have added something to measure the motor speed, a tachometer, and we are comparing that measured speed to the reference input, and we have an error signal. We'll call that E of t. And the controller is going to multiply that error signal by a gain as well. So the controller type will be very similar. It's just an amplifier. But preceding the controller, we do have that subtraction, that comparison between the desired and the actual speed of the motor. So again, I've got EA of t. The output of the controller is a gain factor, K sub CL. So CL is closed loop. And it multiplies not R, but R minus Y. And we have the freedom to choose the amplification factor KCL to be anything we like. It does not need to be the same as K open loop. In fact, it probably will be different. So let's look at what the transfer function of the closed loop system is when I have that controller. So we have Y of S equals, now this here, this A over tau 1s plus tau 2s plus 1, remember, was what the motor does, but it multiplies its input, and its input is EA, which is K times R minus Y from this line right above. So that gets substituted in there. And then I've got B times tau 1s, B over the tau 1 term and the tau 2 term, all times W of S, just like I did before. What's interesting is that the closed loop has introduced for us a Y on the right-hand side. And to get a transfer function, we need to have all the Y's together on the left side. So I'm going to do some algebra to do that. My circling of things has made it a little difficult to see. So first I'm going to say that term just gets copied. There's no change. But then I'll erase this and I'll highlight to see what's going on. First, we've got A closed loop times R over denominator. Gives me A closed loop times R over denominator. And then next, I've got minus Y times A closed loop over denominator. Gives me this minus y times a closed loop over denominator there. So I've simply distributed that the number outside of the parentheses inside the parentheses. And what we want to do is we want to combine the y terms. I've got a y term over here, I've got a y term over there, and I want to bring them together. So I bring the right-hand term over to the left-hand side. And when we do that, it's hard to get it all on the screen. No, we can't quite do it. But I have the y of s times 1, which was already on the left-hand side, and then y of s times the a closed loop over tau 1 s plus 1, etc. That was from the right-hand side that we pulled over to the left-hand side. And then everything else that was on the right-hand side, those two terms remain and simply get copied down. On the left-hand side, I work with that term in the parentheses a little bit to get a common denominator. So I take the 1 and realize that 1 is simply the denominator divided by denominator, so I get the tau 1 s plus 1, tau 2 s plus 1 in the numerator because of that. And I've combined the terms and added them together. On the right-hand side, I have made no changes. Now, what we do moving forward is we look at each term on both sides of the expression and notice that they have a common denominator. So I'm going to get rid of that by multiplying both sides of the equation by the denominator, tau 1s plus 1, tau 2s plus 1. That cancels it out. That cancels that out. That cancels that out. But this numerator term on the left-hand side, I'm going to divide both sides of the equation by that as well. And so that's going to cancel out of the left side but become a new denominator for the two terms on the right-hand side. So that gives me the y of s, isolated all by itself on the left, is a closed loop over a new denominator times r plus b over a new denominator times w. There's something really, really important going on here, and it's probably easy to get lost in the algebraic manipulations and lose sight of it. So I'd like to pause here, slow down just for a second, and note it. We'll note it again in the future, but this is the first time it comes up. If you think about where are the poles of the system, you say, okay, well, the pole is a denominator root of a transfer function. Okay, well, I've got a transfer function here. I've got a transfer function from r to y is this right here. Before we did feedback, we already had a factor denominator, and in fact, it was this one that said I've got one pole at minus 1 over tau 1. I've got another pole at minus 1 over tau 2. It's already factored. But when we did feedback to this system and we found the transfer function, we have a different denominator. The numerator turns out to be the same, but the denominator has changed. I've got a new constant term in here, a times kcl. What this means is that if I were to factor that denominator, so I'd have to expand it all out first and perform the quadratic rule on it to find the roots. But when I found those roots, they would not any longer be at minus 1 over tau 1 and minus 1 over tau 2. They would be somewhere else. So what feedback has done is, without changing the plant in any way, I didn't destroy it, I didn't hit it with a hammer, I didn't adjust some knob on the plant that physically changed the plant. The plant is the same. But by using feedback in a controller, I have made the closed loop system have a different denominator from the open loop system, which means it's going to have different performance. It's going to respond differently, and we're going to take advantage of that. So one thing we can do is we can say, well, what about the final value theorem? Can we figure out what the steady state error is? And we're going to again assume that W equals 0 for now. So that term we are neglecting in our steady state error analysis, but we'll look at it again later when we look at some other things. And we're going to neglect it for the purpose of defining a gain factor. And so what we have is we have y steady state, and we plug in s equals, we say r of s is equal to, this here is equal to r steady state divided by s, because it's a step input, and then we employ the final value theorem, and we get this, that y steady state is a times k divided by 1 plus a times k all times r. And if you want, we could say, well, let's divide top and bottom by a factor. This is 1 over 1 plus a number times r. Now we see that we can't choose a value of k to make the steady state error go away completely. For the open loop system, we could. If there was no disturbance, we chose a value of k that was equal to 1 over a, and our steady state error went away completely. But here it doesn't. But if I choose a really, really big value of k, then 1 over k is about 0, and y steady state then is approximately equal to r steady state. So if I have a high value of that gain, if my amplifier value is large, then I have y steady state is pretty close to r steady state, and I have good tracking. We're going to find ways of designing feedback systems that overcome this limitation, that in fact do achieve 0 steady state error. So we're not too concerned with that right now. What we're more concerned about is going back to the case of, now that we've designed an open loop controller and a closed loop controller with the assumption that there is no load, what happens when there is a load? Does everything fall apart, or do they still work pretty well? So let's look at the open loop with load. And going to the steady state equation, y steady state is equal to a times k open loop times r steady state plus b times w steady state. And we designed these two to cancel out to be 1. A times k equals 1. So I get y steady state is equal to r steady state plus b times w steady state. And if we look at the difference, which I've called delta y, between where I am and where I want to be, I want y to be equal to r steady state, but it's not. It has this additional term here. So the difference, the tracking error, if you will, in the motor velocity because of this load is b times w steady state. Let's look at the closed loop system, and going to its equations, if we find out what is the steady state error, we have y steady state is equal to a KCL over 1 plus a KCL times r steady state, and we just figured that out, plus b over 1 plus a KCL times w steady state. Now here we said if I let k or a times KCL be very, very large, then this first term is close to r steady state. It's not going to be exactly, but it's going to be close. So our tracking error is going to be roughly this. It's going to be more than that because this is not exactly what I want, but it's going to be roughly speaking equal to that. So I have my delta y in this case is equal to b times w steady state, which is what I had before, but now there's an additional term. All of that is divided by a KCL. So when I compare that to that, the closed loop system has the same steady state error except divided by something. So if I'm dividing by a big number, that would be good. And remember, we chose a times KCL to be large, so I am dividing by a big number. So delta y in the second case is going to be much, much smaller than delta y in the first case. So feedback really helps in this situation. If there's a load torque, the feedback helps. So we list our first advantage of feedback here. We have better disturbance rejection by a factor of 1 plus A times K closed loop. Now this should make intuitive sense. We went through an awful lot of math to get to this result, but imagine driving your car and driving without looking at the speedometer and not using any other cues as to what your speed is. And if you've designed for driving on a flat surface with no wind, you know exactly where to put the accelerator pedal, and it's going to go exactly at that speed, and everything's going to be great. But as soon as you encounter a road grade, you're going to not know that the car is slowing down because you're not using feedback. You're going to leave the accelerator pedal in exactly the same place, and your car is going to slow down. It's not going to perform well if you don't measure how well you're doing and then compensate for that in some way. All of us, when we drive, use feedback. We either look at the speedometer or use some other cues of, even sound, the road noise that your car makes gives you some cue that things are not exactly what you wanted, and that causes you often to look at the speedometer. You say, I slowed down, so you push harder on the accelerator pedal and you speed up. So this isn't terribly surprising, but we've now at least shown it for one case that feedback can improve steady state error, and in fact that's going to be part of our design criteria, is to ensure that it does.